Hello and welcome back to Calculus 1 section 4.4 on graphing functions by hand. This is where you can retire your calculators, retire your software and apps on cell phones for graphing, because now you will be introduced to a set of bullet points that need to be computed to graph the function quickly. Is this for basic functions? Obviously not. You should be able to graph x squared and x cubed and square root of x, right? You just know those. This is for more complicated stuff, like, let's say, ln squared of x divided by x minus 3, right? Something like that. So what do we need to know or need to compute? So the list, as I call it, the shopping list. So number one, domain, and I'll put in parentheses and range. Technically, we don't care about the range. Sometimes it's helpful, very, very subtle, right? So it's not a big deal. So domain, that's a huge part. The first thing you figure out is domain. Now the next is an algebra concept of x and y intercepts. That's our number two. So number one is domain, and then number two, x and y intercepts. Number three is going to be all asymptotes. And that's going to be A, vertical asymptote, B, horizontal asymptote, C, slant asymptote. So we have three different types. Number four, we are going to get the first derivative and second derivative. So we'll need those so that we can get first derivative test. And well, let's do just first derivative test. And the first derivative test will give us increase, decrease, min, and max. And then we're going to get second derivative test. So these are the concepts we learned today. And this is going to give us our concavity. And it's going to give us the inflection points. There are other things that you guys can look into. If this stuff is not enough, you can look at symmetry. Not too often, maybe not, right? And 8 additional points. Now, all of this, if we need more info, generally you don't need them. And we'll just say graph. Now you will go, hold on, you said that we have 13 calculations. Yeah, but I grouped 3 asymptotes in the same bullet point, x and a y intercept in the same bullet point. So if you spread this all out and give each one, it will be 13 different things. So all of these you either covered in algebra, pre-calculus, or in our previous lectures. I have nothing new to teach. We just get to apply all of the concepts you guys learned before on a more complicated example, right? The function that we'll start with let's say a rational function and then go from there. So just to test the waters a little bit, let's take a look at something that we could graph without any of these things, but we are going to use them to show that it actually works. So let's go with 6 over x plus 2. Like 6 over x plus 2. What do you know? Well, this 6 is not actually going to do anything. It's just 1 over x. We know that 1 over x has horizontal, vertical asymptote, and then plus 2 is going to move everything up 2 units. So, yeah. We know what this is, but let's let's make it spicier. How about we put x plus 3 in denominator? Let's do that. So now we know it's shifted to the left 3 units and 2 units up. We can do that. All right, so let's take a look at what we can discover here. Well, first of that is domain, right? Domain. That was number 1. So for domain, we know that -3 is a bad point. So we are going to have domain from -infinity to -3, union -3 to positive infinity. So this is our domain. Number 2, as x-intercept, you set y equal to 0. This is algebra 1 concept, right? To find x-intercept, you set y equal to 0. So you have to solve 6 over x plus 3 plus 2 equals to 0. You set your f of x is y, so you set y to 0. And now you have 6 over x plus 3 equals -2. You cross multiply, you get 6 is equal to -2x minus 6. 12 equals -2x, x equals -6. So x-intercept is at -6, 0. Now, this is a point that you will be graphing. So I like to box all of the things that I am going to put on the graph so I can find them quickly. Y-intercept is when you set x equal to 0. So that's going to be 6 divided by 0 plus 3 plus 2, which is 2 plus 2, which is 4. And I have the y-intercept at 0, 4. And that's going to be another box because it is important. So now we have 3. Number 3 for us is to figure out all asymptotes. We have 3 asymptotes. Vertical asymptote. Now, we do have that limit procedure. If anything weird is happening, you're not sure, and so on, you crank the limit. We learned that in 2.4, right? So, but in this case, it's obvious, right? X plus 3 equals 0, x equals -3, which is what interrupts our domain. So that's my vertical asymptote, and I'm going to put the box around it. Horizontal asymptote is we can do the limit x goes to infinity of 6 over x plus 3 plus 2. And when you plug in infinity, this term over here goes to 0. So we have y equals to 2 for horizontal asymptote. If you have a horizontal asymptote, then you can't have slant because they are mutually exclusive. You either have one or the other or none of them, but you can't have both. So as soon as you get the horizontal asymptote, that's a guaranteed you don't have slant. Number 4 on the list after asymptotes was for us to find first and second derivative, and those are just straight up calculations from your chapter 3. So we find the first derivative, and we are going to use that for the first derivative test in the next bullet point. But now we're just going to look for the derivative. So what is my first derivative? Well, I have, you can use quotient rule if you want to. It's going to be x plus 3 squared, and then you have your x plus 3 times the derivative of 6 is 0, minus 6 times 1. So this works out to be -6 divided by x plus 3 squared. Now, it is, for the next derivative, it's better if you write it in line and use chain rule. because using quotient rule with extra chain rule would be annoying. So if you just write it in line like this, you can find the second derivative easier. That's going to be positive 12 x plus 3 to the negative 3. And you can write it as 12 divided by x plus 3 cubed. So now you have your first and your second derivative. I am going to put the blue box around the parts that are the easiest form for you to set them equal to 0. Cool. The next part is to do the first derivative test. So we'll take our negative 6 divided by x plus 3 squared, set that equal to 0, and when you cross multiply, you get negative 6 equal to 0, which is not true. That means that the only partitioning you are going to do is at the vertical asymptote. So no crit points, which implies no min-max. Awesome. So we do the partition from negative infinity to positive infinity, and the partition is at negative 3 because that's where the vertical asymptote is. We pick 2 points, negative 4 and 0. And we do our first derivative test. So f prime at negative 4. That's negative 6 divided by negative 4 plus 3 squared is negative 6, which is less than 0. So we have going down. Yes, I know that 1 over x goes down. So right, it's decreasing. So that's awesome. When we do f of 0, we better get the same answer. F prime of 0 is negative 6 over 0 plus 3 squared. I have negative 6 divided by 9. That's still less than 0. I have another decrease, as I have foreseen, right? And we have no min-max. So that's what we get from the fifth bullet point. Decrease, increase, min and max. Number 6. Second derivative test is going to be when we take our 12 over x plus 3 cubed, set equal to 0, and when you cross multiply, you get 12 equal to 0. Now that's no bueno, right? So again, no solution means no inflection points. But we still have a vertical asymptote. We can still use negative 4 and 0 to do the second derivative test. And that's f double prime at negative 4 is going to be 12 divided by x plus 3, negative 4 plus 3 cubed. Now cubes preserve the sign. So that's negative 1. Cubed is still negative 1. So this is going to be negative 12, which is less than 0, concave down. And then we have f double prime at 0, which is 12 over 3 cubed, which is 12 divided by 27. I don't care what that is. I have positive number divided by positive number. It's larger than 0. I don't care what value. I just need to know that it's larger than 0 or smaller than 0. Concave up. Do I have enough information? Well, let's skip everything else and go directly to the graph to see if we can deal with everything. Now, the key is to have graph paper and to draw big so that you can see all of the things that are happening. We are going to go all the way to the top of the problem and graph our points and asymptotes. X-intercept at negative 6, 0. Okay. 1, 2, 3, 4, 5, negative 6. Y-intercept at 4. So y equals 4, 1, 2, 3, 4. Awesome. Now I have my asymptotes. Vertical asymptote at -3. Okay, that's going to be -3 vertical asymptote. Horizontal asymptote at 2. There we go. And we need to fit the rest of the graph in here. So now, what do I know? I know that the graph is decreasing all the time. How do I draw a graph in this quadrant here, which is decreasing and goes through -6, right? Decreasing and goes through -6. Well, the only thing I can do is follow the blue and red asymptotes while going through 6. That's the only thing I can draw. There's nothing else you can draw that would be decreasing and follow the blue and follow the red, because those are the asymptotes that it has to obey and bend around. It's decreasing. And now, this part of the calculation better be concave down. It is concave down up to -3. Woohoo! On the other side, again, now in this upper corner, I need something that will follow the red, follow the blue as it goes out, and go through value 4, which is our y-intercept. Well, dare I say clearly, I have to draw this. Is that concave up? Of course it's concave up, right? It's a concave up piece. And as you can see, everything, like a puzzle, clicks together, and we have our graph. Ta-da! Done. That's all it is. That's all it is.
So really the only real hard part is getting your derivatives right.
Yes. Annoying part of getting the derivative tests and all of these things in. Yes?
How did you, or why did you say pick those values, -4 and 0, to plug in for the first and second derivative?
We are picking any values in those partitions. You can pick any number. So once you make a partition, using critical points or asymptotes, or inflection points and asymptotes, depending which test you're doing, any point in there will give you the same value. So you can pick -100, and it will give you still concave down, because the calculation here doesn't care about the value you get, it cares about its sign. Because the theorems that we presented say, if the calculation at the test point you pick give you negative, it's decreasing or concave down, depending which test you're doing.
What about functions that have multiple inflection points?
You will have multiple partitions. You pick a number in each partition. So we are going to see problems here that will have, let's say, 3 partitions, 4 partitions, and then you pick in each one, right? Let's see if we can make you happy with the problem. Let's take a look at another one of these that we can grind through quickly. 3x over x squared minus 1. And then the next class we are going to take a look at something with ln, something with trig or whatever. All right, so again, we start with the domain. And domain is from negative infinity to negative 1, union a negative 1 to 1, union 1 to infinity. And number 2 is the x-intercept when you set this equal to 0, right? Because y is 0. Cross multiply, you get 3x equals 0. You get x equals 0. So x-intercept is at 0, 0. Now, anytime you get 0, 0, it's at the same time the y-intercept as well. Because it's the origin. Both asymptotes, both axes intersect there. Vertical asymptote, well, you have your x squared minus 1 equal to 0. You know that you will have x equals minus 1 and x equals 1. Those are your interruptions in domain. So now we have 2 vertical asymptotes. Horizontal asymptote, when you set the limit, x goes to infinity of 3x over x squared minus 1, and divide everywhere by x squared, you get 3 over x divided by 1 minus 1 over x squared. Oops, forgot the limit in front. And this is just going to be 0, because you have 0 divided by 1. I won't put the step in. 0 divided by 1 equals 0. So we have y equals 0, which is the x-axis, as our horizontal asymptote. Now, 4, we have our derivatives. So, the derivative, we use the quotient rule. X squared minus 1 squared, x squared minus 1 times 3 minus 3x times 2x. We simplify that derivative. 3x squared minus 3 minus 6x squared, x squared minus 1 squared. And that's going to be negative 3x squared minus 3 divided by x squared minus 1 squared. Oh, you see this? This is beautiful. Kick out negative 3, you get x squared minus 1. Nice. The first derivative simplifies to negative 3 over x squared minus 1.
Would it be positive 1? To kick out negative 3 would be x squared plus 1.
Oh, yeah. Oh, that ruined it.
Sorry.
No, you are correct. You are correct, my friend. Can't cancel. It's gonna stay this terrible thing. That's okay. Such is life. Second derivative. When you factor out negative 3, that's a plus 1 over there. Well, tears. Negative 3, and then we do the quotient rule. We have our x squared minus 1 to the 4th now, because you have to square it. Then we have your x squared minus 1 squared times the derivative of the top. Now, minus 3 I kicked out, so I don't have to worry about it. So it's just 2x minus x squared plus 1 times the derivative of the bottom, and that's a chain rule. 2 x squared minus 1 times the 2x of the derivative inside. It's a lot of algebra that we have to suffer through over here. Oh, this time I will be able to cancel some of the x squared minus 1s, right? Because I got 2 of those in here, and then minus 4x, x squared plus 1, and x squared minus 1, and then x squared minus 1 to the 4th. So I can cancel one of these and get 3 over there. So what do I have? Negative 3 times. That's going to be 2x cubed minus 2x minus 4x cubed minus 4x divided by the denominator that we don't care about, because when you set equal to 0, it's, well, actually you need it for the test. Negative 3 times negative 2x cubed, because negative 2 minus 4, and then minus 6x divided by x squared minus 1 cubed. So this minus we can factor out 2, make that into a 6, distribute the minus to kill all the other minuses. You just have x. Oh, you can kick out x as well. Kick out x. And what's left is x squared plus 3 divided by x squared minus 1 cubed. I think that's good enough. So minus are all gone. Take out 2 becomes a 6. Take out next against that. Good. And then x squared. Perfect. All right. So now we have our second derivative. We have our mess of the first derivative right there. And we are going to go with the first derivative test. First derivative test, we take and set equal to 0. So I have negative 3 times x squared plus 1. Did we say it's squared? No, just plus 1. Divided by x squared minus 1 squared equal to 0. When you cross multiply, you get negative 3 x squared plus 1 equal to 0. And finally, you get x squared plus 1 equal to 0. You get x squared equals negative 1. No solution. Solutions are complex numbers, but we don't care about complex numbers in calculus. So we are not going to worry about that. And then we are going to do the, so now no min max, right? No min max because there are no critical points. We are going to do our partition now. We have no critical points, so the only partitions we have are asymptotes, and those are at negative 1 and 1. We pick 3 test points because we have 3 partitions, and you pick anything you want in each one of these regions. I'm going to pick negative 2, 0, and positive 2. And now we do the first derivative test for all 3 of these. So f prime at negative 2 is negative 3 times negative 2 squared plus 1 divided by a positive number. Denominator is squared, so every time you put whatever for x, doesn't matter what you put for x in denominator, once you calculate that and square it, it will always be positive, so we don't care. What do we have? We have negative 3 times 5 divided by a positive number. So that's negative number divided by a positive number, which is negative, which means we have a decrease on the first. First derivative at 0 is going to be negative 3, 0 squared plus 1 divided by a positive number. This is also going to be negative divided by a positive. So we are getting another negative value. It's another decrease. And finally, calculation at 2. We're going to have negative 3, 2 squared plus 1 over a positive number is going to be again negative divided by a positive, or another negative. So all of these are negative, negative, negative. Okay. 6, second derivative test. We take our second derivative, which was 6x times the fraction, and the fraction was x squared plus 3 divided by x squared minus 1 cubed equal to 0. So we have 6x equal to 0, and we have x squared plus 3 equal to 0, which has no solution because you will have x squared equal negative 3. So we have now x equals 0, which is inflection point. This is what we just learned about inflection points. And now the partition has a lot more. We have a partition at negative 1. We have a partition at 0. We have a partition at positive 1. So now you have 4 regions. Partitioning is done over asymptotes and critical points and inflection points. Critical for first derivative and inflection for the second. So we did not have any critical points last time in the first derivative test, so we only used asymptotes in a partition. Now we do have inflection point at 0, so we have to use that one, and we have to use asymptotes as well. You always have to use asymptotes if they are present in a partition. So now pick the values, negative 2, negative 1/2, positive 1/2, and positive 2. We have 4 calculations to worry about. So now we have our second derivative computed at negative 2. Well, that's 6 times negative 2, then negative 2 squared plus 3 divided by negative 2 squared minus 1 cubed. And now, because you have a cube, you have to compute, because odd powers preserve the sign. So you have to compute this time. So even powers, they're always positive. But the odd powers are whatever is the input. So we have negative 12 times, on top we have 7, divided by, on the bottom we have 4 minus 1, 3, 27. This is a negative number times a positive number is going to be a negative number. We have a concave down in the first partition. The next problem is negative 1/2. So we have f double prime of negative 1/2. That's 6 times negative 1/2. And then negative 1/2 squared plus 3 divided by negative 1/2 squared minus 1, everything cubed. Half of 6 is 3, so that's negative 3. Up there we have a quarter plus 3, so that's 3.25, I don't care. Divided by a quarter minus 1, that's going to be a negative 3/4. So you see that you have a negative number times a negative number, which is a positive number. You can calculate what it is, but we don't care. I just want to know that it's negative times negative. And if it's negative times negative, it's positive, so concave up on this part. second derivative at positive 1/2, 6 times 1/2, then you have 1/2 squared plus 3 divided by 1/2 squared minus 1 cubed. So this is 3 times, you again have 3.25 divided by another negative number. So now the whole thing works out to be negative because you have positive times negative. And finally, we do this for 2. So we have 6 times 2. Then we have 2 squared plus 3 divided by 2 squared minus 1 cubed. That's a 12 times 7 divided by 27. That's all positive. So we have concave up. They are not guaranteed to alternate, guys. It's not guaranteed to alternate. Function 1 over x squared is like that, and it's concave up, concave up. So it's not guaranteed that they will go concave down, concave up, and alternate. You have to compute every time. You have to compute. So make sure that you are computing these things. Oh, these are short ones. Because we don't have any crazy. I told you each problem is like 30, 40 minutes when you start doing it, because we don't have the speed worked out for this. All right, let's graph, and then if we need extra stuff, we'll get extra stuff. Draw big, first rule of engineering. Draw big. We have some asymptotes. We have maybe some x and y intercept. Oh, x and y intercept, it was a 0, 0, right? Flip like 3 pages back. Okay, so we have our asymptotes at -1, 1, y equals 0, and 0, 0. Okay, great. So here is my 0, 0, x and y intercept. I have my vertical asymptote at -1 and another vertical asymptote at 1. So that's my -1 and 1. There is a horizontal asymptote on the x-axis. And before you scream, hey, but we have the x-intercept, how is it going to? Yes. The function can pierce through horizontal asymptotes. We talked about it in 2.5, and I said wait until you see the cases in chapter 4. Well, you don't have to wait any longer. There's your example. The function is going to cut through the asymptote. Cool. I don't have min, I don't have max, so I would graph those points, but I don't have them. And let's see what I have. I need decreasing functions, so I need a decrease across the board. I know they don't look like this, but what I'm expecting to see is decrease, 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 right? So broad strokes, right? That's what I'm expecting. So now we're going to make them curve by using the concavities. And then I also have to make sure that they're not going to cut through asymptotes on the sides, just in the middle. All right, so what do we get? Let's deal with the middle first, because that's the easiest one. I have a decreasing function, which is supposed to be concave up and then concave down. So if I am to draw a decreasing function as a straight line, and then need to curve it, it will follow the asymptote, and it's going to appear like an inverted x cubed. And you see that between 0 and 1 is concave up, and between -1 and 0. So -1 and 0 is concave up, and 0 and 1 is concave down. And that's exactly what we have here. Concave up towards -1 and concave down towards 1. So we're good on that part. I need a concave down piece and a decreasing function. Let me draw two options on the left. These are the only two options you can draw on the left that are following blue and red asymptote, right? Now, which one of these is decreasing and concave down? The bottom one, right? So we kill the top one, and we draw the bottom one now in black. And again, same kind of thinking here. You can have either this or this. We are supposed to have a decreasing and concave up. The top one, very good. The top one is decreasing and concave up, so we're going to draw. Once you are done with problem, there's only one more step. When you're done with problem, one more step. Yes, because you might care, right? So you go to Desmos or whatever graphing utility you're using, 3x divided by x squared minus 1. There it is. And you know it's good because this is 5, -5, -4, -3, -1, -2, -1, right? -1, there's your asymptote. 5, 4, right? 0, 1, 2, 3, 4, 1. There's another asymptote there. You see that it pierces through the horizontal asymptote because horizontal asymptotes can be pierced locally. We haven't done any problems with E's, LNs, or trig yet, so all of that stuff is going to be covered on a little bit on Monday and a little bit after the exam on Wednesday. So Monday is primarily you bringing in labs. We'll work on labs and we have the review. We'll do another one of these problems just to stay fresh. Bye.